does not. Okay. After rifting off of Asia, India moved northward and collided, or rifting off from Gondwana, collided with Asia. And as it did, it deformed Asia and pushed into Asia, and Southeast Asia sort of wrapped around so that we have the boundaries now to the north and to the east. And on the eastern side, what we have is the same subduction zone that gave us the earthquake in Sumatra. But as you go to the north, the thickness of sediments that's entering that subduction zone becomes on close to 20 kilometers. That produces the very broad fold belt that we see in the Chittagong Hill Tracts, Tripura, and Sylhet that affects that area. But what I'm going to focus on is to the east of that in southwestern Bangladesh to look at the delta and the subsidence. But we will see that the hinge zone and that boundary formed by the rifting plays a part in that. So this is my one equation that I'm going to show you that when you look at the delta, the way I think about it is the sustainability of the delta depends on what the elevation is, and that depends on a mixture of sea level rise, the land rising, various components that produce subsidence and sinking of the land, and then the sedimentation. And what the subsidence does is that increases the effect of sea level rise. The water is going up, but the land is going down. And what's very important is the sedimentation that fills that space. And that balance of subsidence, sedimentation, and sea level holds the key to the sustainability of the delta. Is there enough sediment to counterbalance the subsidence and sea level rise? And how that varies across the delta. So what I'm going to focus on is the subsidence component and trying to understand how large it is and how it varies across the delta. And what we find is that subsidence in Bangladesh comes from multiple causes. This is a schematic cross-section east-west across Bangladesh, where we see tectonics in the east of the fold belt. We can see in the west, the very shallow sediments. And the thing I'm going to worry about most is that within the sediments, there's a lot of sediment compaction and consolidation that is going on, plus the weight of the sediments themselves push the land down as well. And around Dhaka, there's also fluid withdrawal, mostly water pumping, that also impacts subsidence. So just to give you a summary, when sediments get initially deposited on the delta, they're full of water, they're mud and sands. And then as they get buried, the water gets squeezed out and they get turned into rock. And so you can see in this plot, the porosity is very high and then decreases. And as sediments gets pushed down, the water gets squeezed out, and that squeezing out of the water takes place over thousands of years or longer. So that even if you stop putting new sediment on, the land still continues to sink, because squeezing all that water out causes subsidence of the land as the sediments take up less space. And the other thing is that you're piling a lot of sediments onto the edge of this continent, seaward of that hinge zone, and that's causing probably several millimeters a year of subsidence within the basin. So how do we measure subsidence? I've been, working on this for many years. You can see uh, pictures from 2005 and recently showing how much I've been aging going to Bangladesh. Um, so we're using multiple methods of looking at things over the longer time scale of 10,000 years, looking at historic sites to get hundreds of years of subsidence, and then a variety of real-time measurements. Particularly, I've been concentrated on GPS with GNSS, but working with people on rod surface elevation tables, compaction meter, and hopefully in the future, INSAR. And the reason we go for this many different methods is because what we've been finding is that you never get a total picture of subsidence from one type of measurement. And I like to use the analogy of the blind man examining an elephant. Each measurement you make tells you one piece of the story, and we need to use as many different methods as we can because they're all measuring subsidence relative to some reference, and those references are different as I'll show you. So on the longest term, Steve Goodbread, who'll speak after me, has drilled over 500 wells, tube wells in the area to look at the stratigraphy. Here you can see a picture with contours showing the thickness of the Holocene sediments, so the last 10,000 years of sediments. And what you can see is it's very thick along the Ganges, Brahmaputra, and to a lesser extent, the Meghna. And this is because during the last ice age, when sea level was 120 meters lower, those rivers cut deep valleys into the delta, 60 to 100 meters deep. Since sea level rose, in the sediments of the delta have filled in that space. But when we're looking at subsidence, we have to be careful of the sediment accumulation of just filling a hole that was previously made versus actual subsidence. So Celine Grau has looked at the data from these tube wells, and you can see what she found was that to the northwest, there's very little subsidence. And then from that hinge zone on, we see increasing subsidence going seaward to about 4.5 millimeters a year. And this is an average rate over the last 10,000 years. Okay. When we look at historic sites, this was initially pioneered by Mamin Saka from CGIS and Tilhanabuth now in the US. And I've gone and worked on one site, the Shakya Temple in the Sundarbans, where we've reinterpreted that to a higher level of subsidence. I don't have time to go through it in detail, but what we see then is an increasing subsidence. You can see from about 2 millimeters, 3, 4 millimeters, that looks very similar to the Holocene scale. So what that suggests is over the hundreds of year scale and thousands of year scale, the subsidence looks very similar, increasing in a seaward direction. So what I've mostly worked on is GPS. So unlike the GPS that's in your phone, that can tell you where you are to about 3 meters, the ones that we're using, here's a picture of one that's on Polder 32 of the antenna and the receiver. We can get positions for each day that's accurate to about 2 millimeters in the horizontal and about 6 millimeters in the vertical. The way we display it is because this is a 3-dimensional estimate of the position. We show the north, the east, and the vertical. And so in the north and east, you can see that Bangladesh is moving to the north and east with India. as part of the plate tectonics of India still moving into Asia. And we can see that the land is going down. And so each of these points represents, 1 day of measurement over the last now 9 years. Okay. And if we fit this data, including a seasonal component, we can get a rate of how much it's moving to the north and east, about 5.3 centimeters a year. But you can also see the subsidence over here is about 5 millimeters a year. So there is a substantial amount of sinking of the land, and we've set up GPS around the coastal zone to measure this subsidence. Carol Wilson, who I work with, has put in a complementary system called a rod surface elevation table and marker horizon, where they sink a rod up to 80 feet into the ground. So you can see them sinking the rod using a petrol-driven post hole digger. And when it's done, it looks like this. And then when they make a measurement, they attach this rod and make detailed measurements of the elevation around that. And they also measure the accumulation of sediments. And so if you measure the change in elevation and subtract off the amount of sediment that's been deposited, then you get an estimate of how much that land is sinking. But since it only has a rod down to 80 feet or 24 meters, it only tells you how much the land is sinking in that upper 24 meters. For a little bit more, this is something that was done prior to the long-term monitoring project. We installed a series of wells in 2 places. This one is in Vandakot, southeast of Khulna, where in those wells, we drilled the wells from 20 to 300 meters deep, and we installed optical fiber that we stretched, and each week we would attach a laser and measure the length of that fiber, and physically measure how much the sediments were shortening with time. Unfortunately, what happened is you can see over here this riverbank that we're close to, and there's very little river in. In 2015, the Water Development Board dredged the river because boats could only travel on it during high tide, but it destabilized the bank and the equipment collapsed and fell in. And so this equipment is now gone. But it was there for long enough that we can see these measurements. So here in the dark blue dots are the amount of shortening we're seeing in each of them in millimeters a year. And this curve is a fit showing subsidence rate of about 9 millimeters a year. You can also see that the subsidence is occurring, that the sediment compaction is occurring within the Holocene sediments in the upper 100 meters, and there is basically no compaction going on below that. That's because the sediments were eroded down and formed that big valley. And so the sediments is filled up, but until the sediments, the weight of the sediments is larger than it was before, there's no compaction of the deeper sediments. So that what we see is that most of the compaction is happening within just the upper 100 meters of the or less of the Holocene sediments. And so if we put together those measurements, we get these numbers here. You can see these are sites up around Dhaka, and they're showing 9 to 13 millimeters a year of subsidence. Most of that is due to groundwater withdrawal, that the pumping of water out of the aquifer and the depletion of the aquifer is causing subsidence of up to ½ inch a year under Dhaka. we look in the coastal zone, what we can see in these easternmost places, we see 3-4 millimeters a year of subsidence, and these green measurements from the historic sites. These are fairly close to the rates that we're seeing from Graal's longer term measurements. And we think part of that is because the sediments closer to the Meghna River are sandier and there's somewhat less compaction going on. And so we're seeing rates that are similar to the long-term rate. However, if we look at the rates farther west, I should point out that the size of the font is proportional to how long the time series are and how reliable the data is. So the larger numbers are more reliable, and the very small numbers I expect to change over the next few years as we continue making these measurements. It takes many years before you can get a rate accurate to the millimeter level. And so what we see in the West is the most reliable estimates are giving us about 5.5 millimeters a year, but down at Heron Point, we're seeing as high as 8. And I think this is because the sediments farther west away from the river are muddier. The Holocene is also somewhat thicker. And so we're seeing more sediment compaction in that Holocene section. It's giving us rates that are higher than what we see from Graal's paper, particularly in the Sundarbans, which is much muddier. But then when we look at what we are getting from the RSETs that have had a long enough time and from that compaction meter, we're seeing 9 to 10 millimeters a year of subsidence. And so, how do we make sense of that? And again, it comes back to this, what is each system measuring? So the GPS, like the picture I showed you, the antennas are on buildings, and those buildings were all excavated or have some kind of foundation or footings. And so they don't see any very shallow subsidence. Whereas the compaction meter and the rod surface elevation table measure right up to the surface. And so they see any effects that are shallow. And so what we're seeing is this shallow part is we're seeing 9 to 10 millimeters a year. But if we leave out the top part, we're only seeing 4 to 8 millimeters a year. So to further understand that, what we've done is gone to survey of Bangladesh monuments that look like this one. And we've used a campaign system where we put a GPS antenna directly over the monument for 1 to 3, or in some cases up to 5 days. And what you can see below is one of the measurements is that all of these monuments were installed and measured in 2002. So here you can see the elevation in 2002, and here you can see the elevation in 2020, when we made the measurements just before the onset of COVID, and then Hasnat Jaman made some measurements during it. And you can see this subsidence is showing about 14 millimeters a year. And so here are the values in a map. And this is a cross section along this black line. And what you see is in the Northwest, we're seeing very little subsidence. Here, virtually none to a few millimeters a year. And then it increases to 14, 15 millimeters a year. Okay, and above here, I've grayed out that there are a number of measurements where we think the monuments are not stable after 20 years. Some of them may have slumped after they were first installed, and therefore do not give an accurate estimate of subsidence. But we have enough of them that give a consistent pattern that we think this is reliable. And so what you see is the continuous GPS are giving us rates of 3 to 8 millimeters a year. The ArtSets are giving us 9 to 10, and these campaign measurements are giving us 14, 15. And for understanding that difference between what we see in the Northwest and not, we can look. This are some of the wells that Steve Goodbread has drilled, which transects H, J, and K were part of this project. And what they see is on the wells that he did in transect G over here, that the amount of mud is very little, that these sediments are mostly sand. But if you go farther seaward, the sediments are primarily mud. And these measurements are up in the area of transect G. And so we think one is you're closer to the hinge zone, the sediment thickness is smaller and they are sandier, and we're seeing very little subsidence. But as we go farther seaward in the muddier sediments, we're seeing a substantial amount of subsidence that's going on. And if we take a look at how these different measurements combine, what we see is the GPS on the building miss any shallow subsidence that's going on, and they're giving one value. The RODSES and the compaction meter don't measure the deep subsidence, but measure all the way up to the surface. And we think that these campaign GPS measurements are measuring from near the surface all the way down. And so if we combine those, we can start to take a look. And what we're seeing is that very deep, we're seeing 2 to 3 millimeters a year. That's on the same order as what we expect from just the weight of the sediment pushing things down. We see relatively little subsidence below that, or in the intermediate zone. But we see a lot of subsidence in the very shallow area. And so I think this is primarily effective where there's active sedimentation going on, which is where the RSETs are installed, because when you go to those places, there are tree roots taking up space, there are burrows from animals through there, so there's a lot of space in here. And then as the sediments get buried, they lose that space, and you see a lot of compaction that's happening in the upper few meters. And from the historic sites, we also don't get that shallow compaction signal recorded. And so the 1 to 5 millimeters a year is similar to just if you add these two up. And the implications for this are that the subsidence rates for historic sites, sort of 1 to 5, if you look at buildings or the embankments that we're building around the polders, where the site is prepared in some way, where you excavate the ground or prepare some kind of foundation, plus the fact that there's no active sedimentation on top of a building or a polder, we get more of 1 to 8 millimeters a year. But in the open fields and rice paddies, what we're seeing is up to 14 to 15 millimeters a year. And this has implications, for instance, for tidal river management, that if you're trying to refill one of the polders with sediments, you're going to see a lot of compaction in those fresh young sediments. And you're going to need to bring in much more sediments than you think to compensate for the compaction. And if you start to work out the balance of how much sediment needs to come into the delta to counterbalance sea level, the places where there's active sedimentation need more than the places that have been uh, modified by humans. And so we need to take that into account when we take a look uh, at the subsidence rates. So, even in one spot, I cannot give you a single value. We do see the subsidence increasing in a seaward direction and varying from east to west, with more subsidence in the southwestern part of the Delta. But at each site, you need to worry about what's the status of the area you're looking at. Is it a village or an open field? Because the subsidence rates are different and going to vary between them. Uh, I think this is an important and unexpected finding of this additional sense of variation. And right now, I'm hoping that even as this project ends, that we can find the funding and support to continue the work, to continue making measurements with our GPS and with the RSETs, and to do more work to try to understand the lithologic variations and the variations in subsidence that we see, more archaeological sites, and to add INSAR and LIDAR and other measurements as well, to try to add that to the mix of types of measurements that we use to try and understand the subsidence within Bangladesh. Thank you.